What did we do last time? We proved some facts like if A and B are finite, then the Cartesian product is also finite. And moreover, the cardinality of the product equals what? What is the cardinality of the product of two finite sets?
A times B.
The cardinality of A multiplied by the cardinality of B, of course. It is quite clear. From this, we proved that for every natural number n, the cardinality of the nth Cartesian power of A is just the cardinality of A to the power n. Another corollary was as follows. How many functions do we have from A to B when A and B are both finite? The number of functions, the cardinality of the set of all functions is the cardinality of B to the set of the cardinality of A. Is it clear? Another corollary we obtained was as follows. If A is a finite set, we have 2 to the power of the cardinality of A subsets in A. Okay. And now,
excuse me. I have a question from previous lecture about lemma 2, which we were explaining. What is the reason that we can say the lemma was if it's let me bring it for a second. If it's countable and if A is countable and A is an injection to B, then A is finite. I want to know why it's finite. Why not countable?
So what's countable? A is countable.
If A is countable and from A to B there's an injection, then B is finite.
No, of course that's not true. It's not true. If A is countable and A is embeddable into B, then B is infinite. It is infinite. It is infinite, not finite, of course.
Sorry, it was my mistake. It's infinite. Why is that infinite? I don't understand it.
Okay, let's prove it. By the way,
sorry, I don't have problem with the proof. You were intuitively found out that it's
intuitively, the main idea is as follows: every countable set is infinite. Do you agree? Countable means that contains as many elements as the set of all naturals does. So, but A is embeddable into B. What does it mean that A is embeddable into B? That means that there is an injection. There exists an injective function that maps A into B. So B is even greater than A, or not smaller than A. We have an injection. That means that there is a subset, namely the image of A under F, the set of all values of F on A. The image of A under F, this set, is equivalent to A, hence it is equivalent to naturals, to the set of all naturals. On the other hand, this set is a subset of B. So we see that N is embeddable into B. there is a subset, there is an infinite subset in B. But if there is an infinite subset, it is quite easy to prove that B itself cannot be finite. How is it possible that B is finite if one subset of it is infinite? It is countable.
Yeah, I understand. And why cannot we say that B is countable also?
No, it is not necessary so, because here we know that B is greater or equal than A. B might be much greater than A. I'll give you an example. Assume that A is equal to N, while B is equal to R, that is the set of all real numbers. We see that naturals are a subset of reals. Do you agree?
Yes.
As it is a subset, clearly it is embeddable there too. Every subset is embeddable. Here we have a trivial injection, the identity function.
Yes.
But the set of all real numbers is not countable. We know that quite well. Reals are equivalent to the set of all subsets of naturals.
Yeah, I understand. Thank you.
So here, let me reiterate. Here we have just a lower bound on B. B is not less than A. So we know that B is infinite, but it might be it might be much greater than A. So we have no upper bound on B in our assumptions. Is it clear?
Yes, thank you very much.
Okay. But your question is quite useful for our presentation, as here we see an interesting implication that if naturals are embeddable into some set, then the set is infinite. So one may say, one may rephrase this theorem the following way. If naturals are embeddable into B, then, or let's rename it to A, then A is infinite. If naturals or any other countable set is embeddable into A, then A is infinite. But what about the opposite implication? So is it true that if A is infinite, then naturals are embeddable? So if a set is infinite, then there is a countable subset in it, or equivalently, naturals are embeddable. In fact, that's true, and let's prove it. Let's prove it. It will be just a sketch for a rigorous proof. Would depend on the so-called axiom of choice. So we don't want to state it and discuss. So if A is infinite, then naturals are embeddable into A, or equivalently, there is a countable subset, there is C, which is a subset of A, and which is countable. So let's prove it. First of all, if B is finite, for whatever finite B, A minus B is, what do you think about A minus B? What if we throw away some finite amount of elements from an infinite set A? What will we get? What?
Infinite.
Of course, this difference is infinite. We may prove it formally. If this set is finite, if it were finite, then A, which is a union of what? It is a union of A minus B and A intersected with B. It's quite clear. Every element is either in of A is either in B, then it is in the intersection, or it is not in B, then it is it belongs to the difference. So then this set would be finite. For it is this one is finite, this one is a subset of finite B is finite, and we know that the union of two finite sets is finite. Contrary to our assumption that A is infinite. So if the difference is finite, then A is finite as well. So A minus B must be infinite, of course. Okay. And that's true for whatever B. For whatever finite B, if we throw it away, then this will result in an infinite set. Okay. So we see that for every finite B, we may restrict ourselves to subsets of B. For every finite subset B of A minus B is infinite. As it is infinite, then of course this set A minus B is not empty. Do you agree? So A is not empty. Empty set is finite. A is not empty. Hence, there exists some element A0 which belongs to A. But this set, the singleton of this element, is finite. Okay. As it is finite, then A minus this singleton is infinite. It is infinite. As it is infinite, it is not empty. As it is non-empty, there exists some A1 which belongs to this set. By the way, that means that A1 is not equal to A0. Is it clear?
Yeah.
On the other hand, this set of two elements is finite. So we can throw it away from A, which is results in an infinite set, so which is non-empty and so on. Then we may take some A2, which is an element of this set, and of course A2 is not equal to A0 nor is it equal to A1? And so on. So what is the main idea? Our axiom of choice is needed to formalize this and so on. So we take, as A is not empty, we take some element A0. Then we will consider all the remaining elements A except A0 and take A1. Then we throw away these two elements and take A2 and so on. Is it clear? We may do it for every natural number n and put f of k being equal to the case element A we take. All these A's are pairwise distinct, hence f is injective. As every number ak is distinct from any previous one. So it is injective. Hence, we've got an injection from naturals to A. Is it clear?
Yeah.
So, what do we have? We see that if a set is infinite, then we may repeatedly take elements from it. So taking these elements, pairwise distinct, we obtain an injection from naturals to A. So these two statements taken together means that a set is infinite if and only if naturals are embeddable into it. So we have the following theorem. For every A is infinite if and only if there is an injection from naturals to A. This is a positive characterization for infiniteness. So by our definition, infinite means not finite. So there is no bijection with any n underlined, with any natural number. But now we see that infiniteness means that there is an injection from all naturals to our set. Is it clear?
Yeah.
So, and now let's do some combinatorics. First of all, assume that A, B, C, and so on, all sets we want to consider are finite. How many functions from A to B do we have? How many functions?
B power
B to the power A. Of course, say, what if we have, say, 3 to the power 2? How many functions do we have? We have 9 functions. Why is it so? Because here we have 0 and 1. And for 0, assume we want to specify our function. We have 3 ways. We have 3 ways. I want to prove it in formula. We have 3 ways to choose the first value, f of 0. And for every choice, for each choice of the first value, we still have 3 ways to choose the second value. So this results in 9 ways to choose 2 values. To choose a pair that characterizes our function. Is it clear?
Yes.
So
Yes,
we have 9 ways, and this is true for every function. But now let's count injections.
Excuse me.
Uh-huh.
We had this last session, and you gave a formula for 3x plus y. And I wanted to understand how is it possible to make this formula for other numbers, for example, 4 and 7, something like that.
Which formula?
You said you gave an bijection, and for x and y, which there was a bijection to 3x plus y, which you wanted to prove the rule of products. And then you said, yeah, all of the, I wanted to know how is it possible to make such a formula for other numbers, for example, 4 multiplied by 7, like that.
So, assume that we have 4 and 7.
Or if it's a big number, maybe less
And we want to construct a bijection between pairs and elements of this set. Okay, let's do it. Here we have pairs. Which pairs? 0, 0, 0. What else? 0, 1, 0, 2, 0, 6. What else?
Yes. 1, 1, 0, 1, 1 to 7, 1 to 6. Sorry. Yes.
So here we have these pairs. Is it clear?
Yes.
Okay. And now, in general, here we have some pair xy, where x is from 0 to 3, and y is from 0 to 6. Do you agree?
Yeah.
Okay. And now let's do the following. Let's map this pair to the following number: x multiplied by 7, or better, 7 multiplied by x, which is the same, of course. 7x plus y. Let's map this pair to such a number. What can you say about this number? What is the greatest possible value for it?
27.
7 multiplied by 3 plus 6, which is
27.
27. So this number is between 0 and 27. Is it clear?
Yes.
It's possible to prove, basing on the integer division theorem, that every number from 0 to 27 is uniquely expressed this way. So this is our bijection. Say 0, 0 maps to what? 7 multiplied by 0 plus 0 to 0. 0, 6 maps to 6. 1, 6 maps to which number? 7 multiplied by 1 plus 6 to 13, and so on. 3, 0 maps to 7 by 3 plus 0 to 21. And this one, of course, maps to 27. This is a mapping of our pairs to first 28 numbers.
Yeah, I understand. Thank you.
Okay.
So the formula will be always the coefficients of x and plus times x plus y, right? Always like that.
If these sets are n of the form n underlined m underlined, then it will be so. But it might be possible that our sets are not exactly of this form. Assume that A is not 4 underlined, but has 4 elements. Then we must employ some bijections we have between A and 4 underlined and B and 7 underlined. Then, if we have some element from A times B, then the formula will be as follows. Our pair AB would be mapped to the following number. 7, that is the cardinality of B. The cardinality of B multiplied by what? Multiplied by not our A itself, as it might be not number, but by its image in the set 4 underlined, plus the image of B in the set 7 underlined. This is a number, and this is another number. Is it clear?
Yes. Yeah, I understand. Yeah.
So, in general, your sets might not be exactly 4 underlined, but something equivalent to it. Then you have to employ your bijections between A and 4 underlined and so on. Is it clear?
Yes. Yeah, it's clear. Thank you.
Okay. And now let's count injections. Assume that we are interested in not all functions, but just injections. Is injective. How many injections do we have between two finite sets? Okay. Let's start with an example. How many injections do we have from 2 elements to 3 elements? Of course, that's clear that it is not no more. We have no more injections. Then we have functions in general, as every injection is a function. So there should be this inequality. Is it clear?
Yes.
Yes.
So we have no more then 9 injections. But how many injections do we have indeed? Indeed, we have 6 injections. Let's see why. Okay. Let's describe our injection with this tree-like structure. How many ways are there to choose f of 0?
3.
3 ways. F of 0 might be 0, 1, or 2. Is it clear?
Yes.
If f of 0 is 0, what can f of 1 be?
0, 1, or 2.
No, it can't be 0, as f must be injective.
Oh, so 1 and 2.
Of course, if f of 0 is 0, then f of 1 is either 1 or 2. So we have 2 ways to choose it. If f of 0 is 1, what can be f of 1?
0, 2.
0, 2. If f of 0 is 2, what can be f of 1?
1 and 0.
Oh, of course. So, anyway, in any case, we have 2 choices for f of 1, given some choice for f of 0. And in general, we have how many choices? 3 choices for the first value, and for any choice of the first value, we have 2 choices of the second value. Is it clear?
Yes.
We have 6 injections, and we see that our injections are in one-to-one correspondence with, of course, with the tuples of their values, like 0, 1, 0, 2, 1, 2, 1, 0, 2, 0, 2, 1. And these tuples form a subset of the set of all tuples. But which subset? It is a set of tuples where the coordinates are distinct. So it is a set of all possible tuples of the form A1, A2, where A1 and A2 are distinct. Is it clear?
Yes.
By the way, such tuples have a traditional name. Such tuples without repetitions are called traditionally arrangements. They are called arrangements.
So you wrote such tuples, what?
Without. This is
Okay.
standard. Without.
Oh, okay, so it's fine.
Such tuples without repetitions are called arrangements. So we have an arrangement of 2 elements of length 2. Okay. But now let's count them more systemically, in a systemic manner. Okay. How is it possible to count all injections from 2 underlined to 3 underlined? First of all, I want to state an important combinatorial principle, which is used widely but rarely discussed. I'll call it the following way. Lemma 1, just the size matters. Just the size matters. What does it mean? That means that if you want to count some combinatorial structure elements like injections between two finite sets, then just the number of elements in your sets is relevant, not the nature of this element. So if A prime is equivalent to A, that is, they have equally many elements, and B prime is equivalent to B, then you will have as many injections from A prime to B prime as you have injections from A to B. Is it clear? Just the size of our sets matters. If A and A prime are of the same size, we will have as many injections between A and B as we have them between A prime and B prime. Is it clear?
We can also say A prime injection between A prime, for example.
I don't quite understand. So what can you say?
Injection between, you wrote injection between A prime and B prime. I wanted to say if it's possible to write it injection between A prime and B.
Okay. First of all, this is not one injection, but the set of all injections. But anyway, of course, this set is still equivalent to this one. Of course. Why is it so? Because we may apply our lemma and notice that B is equivalent to B. Yes. It is just the same. It's just the same statement. A particular case where B and B prime are the same. Is it clear?
Yes.
Okay, let's prove it. We will need many results of this form, but I'll prove it just once for this particular case. So, I want to prove that there are as many injections between A prime and B prime as we have injections between A and B. So what do I need? I need a bijection. I need a bijection theta. Let's use Greek letters, theta. Such that theta is a bijection between the set of all injections from A prime to B prime and the set of all injections from A to B. Okay, that's easy. What do we have? First of all, I have that there is an injection, a bijection phi from A prime to A. There is a bijection psi from B prime to B. I have them. So let's make a diagram. Here we have A prime and the bijection phi from A prime to A. Here I have B prime and the bijection psi from B prime to B. Assume that I have some injection F from A prime to B prime. What do I want? I want to make somehow a an injection theta of f from A to B. Do you agree?
Yes.
Okay. How is it possible to construct such injection? What is the easiest, the most obvious way to do so? Here in these questions, in questions like that, the most easy way is the best. You know that any composition of injections is an injection. Which composition is an injection from A to B? Is there any natural function from A to A prime?
Phi?
No, not
Image of
exactly phi. Phi is from A prime to A, but
Image of phi.
not image, but the converse of phi. The converse of phi is from A to A prime. So we see the following paths in this diagram. The converse of phi, f, and then psi. So the composition of these three functions will be a function from A to B. Do you agree?
Yes.
It is injective. Why is it injective? Because phi converse and psi are bijections. If they are bijections, they are injections, of course. So we have construct an injection from A to B. The only remaining point of interest is to prove that this theta of f, that theta is a bijection. So if f and g are distinct, then theta of f and theta of g are distinct, and so on. Okay, let's check it. Theta itself is injective. Of course, it is abstract. It is a function which takes a function and returns a function. But nevertheless, we are doing some mathematics here. So abstract, we shouldn't be afraid of abstract. Okay, let's prove that theta is injective. What does it mean? I want that if theta of f equals theta of g, then there should be f being equal to g. Formally, that is for every two injections, f and g from A prime to B prime. Is it clear? Is it clear? Dear students.
Yes.
And now, let's assume that theta of f indeed equals theta of g. So what does it mean? By the definition of theta, that means that these two compositions are equal. Okay, they're equal. And what can we do? Let's do some trick. Do you agree, by the way, that this composition is just the identity function?
Yes.
We know that for a bijection, its composition with its converse is the identity function. Do you agree that the composition with the identity doesn't change a function?
Yes, yes, exactly.
So what do we have? What is f? F is the same as this one. Multiplying by identity changes nothing. Is it clear?
Yes.
Okay. Let's expand this to according to these equalities. And now we recall that our composition is associative. So we may regroup, we may regroup them. Do you agree? But what is that?
Yes, yes.
It is theta of f. As it is theta of f, it is the same as theta of g. And then we will do all the same, but in the opposite direction. Here we have psi, g, the converse of phi, and so on. All the same, but just in the opposite direction. So f equals g. Is it clear?
Yes.
And now I want to prove that theta is surjective. What does it mean? Theta is surjective. That means that for every injection H, from A to B, there exists an injection F from A prime to B prime such that theta of F equals H. So now we are given with some H. We are given with H, and we want to find F so that theta of F equals H. But what is theta of F? It is just this one. It is just this one. Okay. What should I take as F? H is given. It's quite clear. Let's take H. Let's take such a composition. FH, the converse of psi. What is it? Phi phi leads us from A prime to A. H leads us from A to B. And the converse of psi leads us from B to B prime. Is it clear?
It is. Yes.
So this composition is indeed an injection from A prime to B prime. The only thing I need to check is this equality. Excuse me, this one. Okay, what is theta of F? Theta of F is just that. After regrouping, I'll obtain a H multiplied by identities. So it is just H. Is it clear?
Yes.
So I proved that just the size matters when counting injections. There are as many injections between A prime and B prime as there are injections between A and B, if, of course, A and A prime and B prime are of the same size. That means that it is enough to count as every finite set, you know, A is finite. A is finite if and only if A is equivalent to some n underlined. That means that it is it's enough to count only injections between sets of the form n underlined and m underlined. Okay, let's do that. My theorem will be as follows. For every two natural numbers n and m, the number of injections from m underlined to n underlined equals. It equals 0 if m is greater than n. By the way, do you remember the pigeonhole principle?
Yes.
And it equals n factorial over n minus m factorial. If m is less or equal than n. By the way, do you know what a factorial is? What is the factorial of n? It is the product of all numbers from n to 1. And the factorial of 0 is by definition
1.
1. So factorial is recursively defined by these two equations. What is this number? N factorial over n minus m factorial. Let's see. What is it? N factorial is a product of all numbers. N minus m plus 1, n minus m. You know, m is less or equal than n here. This is the numerator. And what is the denominator? It is just that. Do you agree?
Excuse me. What was the reason that you said by the pigeonhole principle?
Pigeonhole principle is needed for the first branch. That there is no injection from a greater set to a lesser set.
Yes.
By the way, is this equation clear?
Yes, it is.
So I can cancel these numbers. And what do I see? I see that the number of injections according to this formula is just the product of the first m numbers. So here we have m factors in this product, starting from n and going downward Is it clear?
Yes.
Say, what is the number of injections from 2 underlined to 3 underlined, which we have computed earlier. We have computed earlier to be equal to 6. What is it according to our formula? Let's see. It is n, that is 3, multiplied by n minus 1, multiplied by 2. 2 factors of this form. It is 6. Is it clear?
Okay.
Okay, let's prove this theorem. The first case, if m is greater than n, then we have no injection by the pigeonhole principle. The pigeonhole principle says that it's not possible to embed m underlined to n underlined when m is greater than n. Do you agree?
Yes. Yes.
So in this case, we have 0 injections, no injections at all. And now assume that m is indeed greater than n. Excuse me. Assume that m is less or equal than n. What then? Then I'll apply induction. I'll apply induction. Let's do induction on m. So what do I want? I want the following. I want to prove the following statement. For every m, for every n, if n is greater than m, then the number of injections from m to n equals n underlined divided by n minus m underlined. So this is my statement, which depends on m, which I want to prove by induction. Is it clear?
Yes.
Okay. The base of the induction, m equals 0. Ha! Now, m underlined is 0 underlined, that is the empty set. How many how many injections do we have from the empty set to whatever set?
Nothing. It's empty.
No, we have one. The empty set of pairs is a function, and this function is injective.
Sorry, repeat it, please, again, what you said.
How many injections do we have from the empty set to any set?
Only empty sets?
Of course, we have one injection, the empty set of pairs.
Yes.
The empty set of pairs is a function which is injective, for it doesn't glue any two distinct elements together. So we have one injection. Is it clear?
Yes.
And now let's prove the inductive step. I want to state the inductive hypothesis, which says that, what is my hypothesis? For M, everything is okay. For M, if N is greater or equal than M, then there are that many injections. There are that many injections. What do I want? I want the same, but for M plus 1. I want all the same, but for M plus 1. Is it clear? Okay. And now, let's assume that N is indeed greater or equal than M plus 1. Of course, that means that N is greater or equal than M. Is it clear?
Yes.
And now, let's consider the set of all injections from M plus 1 to N. I want to compute the number of injections or the number of elements in this set. Okay. What if F is an injection from M plus 1? Please switch off your microphone. If you don't want, thank you. What can you say about such an injection? We know that in M plus 1, there is the greatest element. Which is the greatest element in M plus 1? M plus 1 is a set of all naturals from 0 to M plus 1 underlined.
To M.
To M. So, and besides that, if we throw this element away, we will obtain the set M underlined. Do you agree?
Yes.
And our M is mapped to some K. Let's classify our injections according to the values they take at the point M. Xk will be the set of all injections which take K at M. What can you say about K? What are the possible values?
Only one.
K may be anything from 0 to N minus 1, any element of N. Is it clear?
Yes.
By the way, so we have that the set of all injections is just the union of these sets. Do you agree?
Yes.
But are these sets pairwise disjoint? Clearly they are. If K is not equal to L, then XK and XL are disjoint. Why? Because it is not possible that a function takes two distinct values at the same point. Is it clear?
Yes.
So we have a finite union of finite sets. By the rule of thumb, the cardinality of X is then such sum of cardinalities. Is it clear?
Yes.
The only thing it remains to clarify is the cardinality of xk, that is the number of injections which take k at m. Ha! Interesting. That's interesting. Assume that f is such an injection. What can we say about that? What if we throw away the pair mk from it? What is it? It is some set f prime. What can we say about f prime? F prime is all pairs from f besides this one, mk.
Injection, the set of all injections from M.
Surely, f prime is an injection. But where from? Of course, it is a function.
M
it is injective because it can't glue any two distinct elements together. It is just a subset of f. It is an injection from M underlined. Do you agree? It maps all the elements besides M itself. It is an injection from M underlined to which set?
N underlined.
N underlined, but we can strengthen that to N underlined without K.
K.
Without K, it doesn't take K as a value because F is injective. If F takes K at M, it can't take K at any other point. Is it clear?
Yes.
On the other hand, we see that F is F prime union MK. Do you agree?
Yes.
So one can restore F from F prime. So in fact, it is easy to see that we have a bijection between our xk and the set of all injections from M underlined to N underlined minus K. This injection is just a mapping, the mapping from F to F prime. Is that point clear? It is the finest point of the whole proof. We say that our injection is completely determined by its part, its restriction to M underlined. Is that thing clear?
Sorry, I didn't understand the last part, which you wrote xk is equivalent to injection.
It is equivalent to the set of all injections from M underlined to N minus K. Why is it so? Because I can provide a bijection theta, namely this one.
Sorry, what was xk was
Xk was the set of all injections from m plus 1 underlined that take to n underlined that take k at m.
k at m.
K at m, the value at m is some fixed k. Let's consider all such injections whose value is k.
Oh, I understand. Yes.
So, but every such injection is uniquely determined by its values on all the other points. Is it clear?
Yes, thank you.
There are as many such injections as there are injections from m to n minus k. But how many injections do we have here? We know that just the size matters. So we have as many injections from m underlined to n minus k as we have them from m to which set? n minus 1 underlined. Why? Because n minus k has exactly n minus 1 element. Is it clear?
Yes.
Yes.
But this number is known to us. Why? That's easier. We know that m plus 1 was greater or equal than n. M plus 1 was greater or equal excuse me. That's not true. N was greater or equal than m plus 1. This was our assumption. But that means that n minus 1 is is greater or equal than m. Do you agree?
Yes.
And now let's look at our inductive hypothesis. Our inductive hypothesis says that for every number which is greater or equal than m, we have such a formula. Let's take n minus 1 as this number. Is it clear? For every number which is greater or equal than m, n minus 1 is greater or equal than m. Then, by the inductive hypothesis, I have that there are this many n minus 1 factorial over n minus 1 minus m factorial injections. Is it clear?
Yes.
So this number is known, and xk, for whatever k, this is the trick. The k doesn't matter. The value of k doesn't matter. For whatever k, we have that the cardinality of xk equals this number. Ha! That's almost all. So xk has this many elements. And on the other hand, the set x, that is the set of all injections we're interested in, is just the sum of n summons of the same size. It is the size of x0 plus x1 plus x n minus 1. So here we have n multiplied, as we have n summands here, n multiplied by this value. N multiplied by n minus 1 factorial is what? N factorial over, let's regroup, n minus m plus 1 factorial. So we've got that the number of injections from m plus 1 to n is exactly this. N factorial over n minus m plus 1 factorial. So that's it. N minus m plus 1. Is it clear?
Yes.
Okay. As I've established this step of induction, by the principle of induction, I see that this statement holds for every m. So I've proved my theorem. In fact, let's give an intuitive proof for the same, with the same result, of course. Let's give the intuitive proof. I want to specify an injection. I need an injection from m underlined to n underlined, where, of course, m is less or equal than n. Otherwise, there is no injection. M is less or equal than n. First of all, I have to specify f of 0, the first value. How many ways I have to do so? What can it be? F of 0.
N.
It can be anything from 0 to n minus 1. Is it clear?
Yes.
I have n ways to do so. Okay. Assume that our first value is 0. What can my second value be? Anything from 1 to
N minus 1.
To n minus 1. So I have, here I have n possibilities, n choices. And here I have n minus 1 choices in this case. And what if it were 1? Then it can be anything except 1, 0, 2, and so on. And if it was n minus 1, here I have anything from 0 to n minus 2. Anyway, I have n minus 1 choice. Is it clear?
Yes.
And what about f of 2? How many choices do I have here? If f of 0 is 0, f of 1 is 1, say, what can I take here? Anything from 2 to n minus 1. So I have n minus 2 choices. Is it clear?
Yes.
And so on up to f of m minus 1, where I will have n minus m minus 1 choices. Multiplying, I'll obtain n multiplied by n minus 1 multiplied by n minus 2 and so on multiplied by n minus m plus 1, which is just our number n factorial over n minus m factorial. Is it clear?
Yes.
Yeah.
But I've done it formally using induction without any words like and so on and so forth. So I see that I have exactly this number of injections between an M element set and N element set. And the last point is as follows. Let's recall a useful theorem. We know that for every two finite sets A and B, if A and B are of the same size, then any function from A to B is injective when a function between two finite sets of the same size is injective. You'd better memorize this statement and do not forget it. When a function between two sets of the same size is injective.
Bijection.
It is surjective or bijective. So I can restate it the following way. F is injective if and only if it is bijective. Do you remember that? Every function between two finite sets of the same size is injective if and only if it is bijective. Every injection is a bijection if the size is the same. Is it clear? Is it clear? So the set of injections from n underlined to n underlined is the set of bijections. Every injection is bijective, and the opposite implication is trivial. Every injection is bijection, so bijections and injections between two sets of the same size are the same. So in particular, we have the same number of injections as we have for bijections. So the number of bijections from n to n is n factorial over n minus n factorial, or n factorial over 0 factorial, and 0 factorial is what?
1.
Is 1. So we have this many bijections on a set. There is n factorial bijections. From a set to itself. Is it clear? Assume that our set has exactly 3 elements. Let's call them A, B, and C. Which bijections do we have? Of course, for example, how many bijections from 3 to A do we have? How many? 3 factorial is is 6. We should have exactly 6 bijections. Let's enumerate them. First bijections: 0 to A, 1 to B, 2 to C. What else? Please give an example.
0 to B, 1 to A, and 2 to C.
What else?
0 to C, 1 to A, 2 to B.
By the way, we know there are, of course, 3 more examples. We know that every function from 3 to A might be described the following way: as a tuple of its values. Is it clear?
Yes.
So likewise, we can describe our bijections as the tuples of their values. For the first one, the tuple is ABC.
ABC.
For the second one,
BAC.
For the third one,
CAB.
Please name the remaining 3 tuples.
BCA.
BCA. Okay, what else?
ACB.
One more.
And
CBA, of course.
CBA.
So we have 6 tuples. These tuples are the same as our bijections, of course. And these are arrangements of 3 elements, of length 3 of 3 elements. Such arrangements are usually called permutations. These are called permutations. Permutations of the set A. So a permutation is almost the same as a bijection. It is a reordering of all our sets of the elements of our set. Is it clear?
yes.
So what is the number of permutations? The number of permutations of the set A is the same as the number of bijections from n underlined, where n is the cardinality. So it is just the cardinality, the factorial of the cardinality of A. Is it clear?
Yes.
If we have an n element set, we have n factorial ways to order it. We have n factorial permutations. Is it clear?
Yes.
So as for now, we can count bijections between 2 sets of the same size. Of course, there is no bijection between 2 sets of different sizes. We can count functions in general, and we can count injections. Our next point for the next lecture, of course, is counting subsets. We know that in general, in an n element set, we have 2 to the power n subsets. But how many subsets of, say, 3 elements will we have there? We shall count it next time. And then after seeing some combinatorics, we will move to orders, abstract ordering, spatial orders, and equivalence relations, and then probably we will do some logic, consider Boolean functions, and maybe some formal logic, or maybe even algorithms. We shall see.